So you have me again. Sorry about that. It's Philip's fault. I'll try to be brief. All right. So I'll be summarizing a little bit what is the Fab4, and then extend to some work I did as well with Prado Martin Moruno and Francisco Lobo. You've seen these already. Has anyone not seen these by now? Of course they're not. All right. So the Horndeski Lagrangian looks a bit messy, but it turns out that in FRW, it takes a really simple, well, it looks simple. It looks like a simple expression here. Okay, you can split a part that does not depend on curvature and a part that depends on curvature. And this is what these people, Charmozy is also here from Paris, he did with other people in Nottingham. Yeah. So, and they sort of finding a way to solve the cosmological constant problem, or maybe better saying, the vacuum energy problem. And that's the recipe for it. And summarizing it in concept, this is what it means. We want to find a theory that admits a vacuum for any value of the cosmological constant. And this should remain true before and after a phase transition, where the cosmological constant jumps instantaneously by a finite amount. Okay, so we want cosmological constant, or the vacuum energy, can change whenever there is a phase transition and you want to cancel that out. Okay, and a theory must allow for non-trivial cosmology. I mean, you must have a viable cosmology out of this. So this is the concept. This is what they're looking for. And in physically, I mean, in terms of, well, physical quantities, this is what it means. The field equation must be trivially satisfied at the critical point to allow the field to self-adjust. I mean, this means that there's a, say, on-shell Lagrangian at the critical point that only depends on A, does not depend on phi dot or phi. Okay, so that's the first idea. And then at the critical point, the Hamiltonian must depend on phi dot, so that the continuous field can absorb discontinuities of the vacuum energy. So we want an Hamiltonian, that means a Friedmann equation that depends on phi dot, so that when there is a change in the vacuum energy, this phi dot cancels out this change. Okay, and the scalar field equation of motion must depend on h dot, such that the cosmological constant, so the cosmological evolution, is non-trivial before screening. So essentially, we want something cosmology that is viable. Okay, so this is the recipe. In terms of equations, going back to the Lagrangian, the way it was written before, maybe I'll bring it back again, written like this. By the way, these x and y are related, obviously, to the G1, G2, G3, G4. Actually, there's no G2. G3, G4, G5 equations in the Horndeski Lagrangian. All right. So, in terms of equations, this is what it means: that at the critical point, the Lagrangian only depends on A up to a total derivative. Okay, and then from the requirement that the Hamiltonian depends on phi dot, must depend on phi dot, so differentiated with respect to phi dot and requiring that it's not equal to 0, this derivative is not equal to 0, you get this constraint. And then at phi dot, or actually the equation of motion depends on phi dot, on h dot, then you get this extra constraint. Okay, so this is all Charmozy's et al. So from these requirements, from this recipe, they obtain what he called the Fab4. So these 4 terms of the Lagrangian with these potentials, J, P, G, and R. Okay, which obviously you know what they mean, right? So they also require that the cosmological models approach a patch of Minkowski with k equals -1. Okay, so curved space. Right. So the problem here is that these potentials here, John and Paul, they represent, or they mimic, a stiff fluid, and George, radiation, and Ringo, curvature. So this doesn't seem that there's a viable cosmology coming out of it. Certainly we don't find something that is dominated by the radiation, matter, and then a cosmological constant. Anyway, remember the attractor is a curved universe. Okay, and that's not a problem. It's Minkowski with a curved universe. So it's unclear how to obtain a late time accelerated universe. And starting from this, and using these prescriptions, or these 3 prescriptions, we tried to build a model that leads to a late-time de Sitter evolution. Okay, so the idea is that we don't want Minkowski, we want de Sitter, and we don't want a cosmological constant put by hand. We want the late-time de Sitter solution to be a consequence of the Lagrangian. Okay, so it's a parameter of the model, not a matter fluid. Okay, so basically that's what it is. That's what I'm saying in there. Right. So we want the critical point to be described by lambda, and this is a big step now. But this requirement here means that at the critical point, the Horndeski Lagrangian as is looks like this. Okay, it depends on this function in this way, the h and h phi here. Okay, it depends linearly on phi dot. Okay, this phi dot comes from the total derivative that you saw before. Okay, so there are 2 ways of building a Lagrangian like this. Okay, so this x, because now we want flat universe, k is 0, so this quantity k times y is 0. So you only have these the axis, and at the critical point means when h, the roll rate is lambda, then we have this. There are 2 ways of getting this from x. Or x has the same form as this, is written in terms of these 2 functions that will be related like this at the critical point. Or x are nonlinear terms in phi dot, and which contribution must vanish at the critical point, so that we obtain these back at the critical point. Okay, hope more or less you see the idea. Okay, so that's how we constructed this Lagrangian. So looking first at the linear models. Anyway, these we call the linear models, and then the nonlinear models are more general. The linear models, so which we wrote like this, Lagrangian, the total Lagrangian will be this, and then because at the critical point they have to have that aspect, that they look in a particular way, then there's a constraint between these functions. So there are, because we sum from 0 to 3, there are 4 of these, there are 8, there's 1 constraint, so there are 7 free functions. If they call them fab 4 to the other functions, we call these the magnificent 7. Okay, Mach 7. Okay. So, right, and okay, so this is the dynamical system in terms of h and phi. We can of course talk a lot about this. There are several cases we considered, but there's one particular where the potentials are written like this, and there's a reason why we wrote them like this, that seem to lead to a viable cosmology, more or less. Yeah. So this is, it looks like scaling, and then the scalar field dominates. Yeah. So this is a scalar field, radiation and matter. So it looks more or less okay, but you can see that actually that at early times there's early dark energy, and this is severely constrained. So this model is almost what we want, but it's not exactly. So you look at the nonlinear models. So this axis that becomes 0 at the critical point, and in this case, of course, there's still a constraint between them, and this is the dynamical system. And of course, there's a lot we could say here, but I promised I would do this in 10 minutes. So this is an example of an evolution that looks interesting. Okay, so this, now we don't have early dark energy anymore, and we have an equation of state parameter today that is very close to -1. Okay, so it seems that we can, yeah, that's it. So it seems that we can build models that are in principle viable. Okay, and they lead to what we want and parameters that are in accordance with the current observations. Okay, like the equation of state parameter, so it's very small and it evolves very slowly. More recently, Prado, Martin Moruno, and Cristiano Germani, they wrote another paper considering this coupling that you can see in Horndeski Lagrangian, and the conclusion is that they've shown that there is a tracking trajectory. And in their words, no matter what the initial conditions are, the field will asymptotically tend to that trajectory. Okay, so it means that that's on the evolution to the de Sitter attractor. There's this evolution is itself an attractor. Okay, it's independent on the initial conditions for this case at least. Okay, so I think there's something promising here. We need to look at other cases. Need to study perturbations, obviously, and you should look at the combination of having both the linear models and nonlinear models. And so on the first aspect, we're already taking care of it with Miguel and some other people. in Lisbon, and not only. So I hope it was helpful, and if you want to discuss.
Thank you. You can have a couple of questions if you have. If not, we'll get you lunch, and you're free to discuss.
Of this thing,
Covariantly, no, I mean, it's your Horndeski Lagrangian.
You picked some functions. I mean, right? It's hard for me to.
No. Probably try hard, but no. We look no. Then we look at FRW. That's it. Because in the Fab4 it's nice actually. They wrote in a nice way, but here it was not really easy.
For the model we're looking at, you have a choice of functions, and it involves G3 and G4 in some combination with some square root of x.
Yes, I don't remember the exact expression, but we looked at this in the paper and afterwards. And of course, you can write this in terms of G3, G4, and G5.
Okay.
Right. This example I had here, right? This example here. It's actually simple. I mean, this basically it's x. This phi is x. Right? Or actually, it's inverse of x. Okay.
Could you do it without G4? So that you don't.
I don't remember. Actually, I don't remember the expressions. We discussed this. I don't actually. I meant to have a look before the presentation, but I forgot about it. Maybe.
But it's okay. Only if it's G4 or G5.
You're safe for a month or so.
More comments or? Okay, thanks a lot again, and we'll go to lunch in a few minutes.